Hello and welcome to Lecture 4 for the course ECE 1B, Computer Engineering Freshman Seminar, entitled 10 Puzzling Problems in Computer Engineering. Today's topic, as you see from the title slide, is cryptography. Now, an interesting aspect of this topic is that I don't really have to make up puzzles and then connect them to actual computer engineering applications because cryptography itself starts with puzzles. These are basically secret messages, secret codes that are used to communicate between individuals securely. In other words, if a message goes over a communication network, and somebody intercepts it, if it's encrypted, that intercepting person will not be able to understand the meaning, and only a person with knowledge of how the encryption was done will be able to decrypt or decode the message. So basically, actual applications in this area are puzzles in themselves. So that will become clear as we go through the topics of the lecture. So first, let's note that this type of puzzles of trying to decode messages, sort of a daily occurrence in people, in the life of people who work in archaeology. They discover a tablet, such as the one shown in this figure, and there are some symbols written on it. If this is the first time a tablet with this particular set of symbols is discovered, the language is unknown. Conventions of the language and the meaning of symbols is unknown. So basically, archaeologists or people working with them have to figure out what these symbols mean, and what message was written on this tablet and what is its historical significance. Well, sometimes we discover tablets that are partially intact. They have broken parts like the one shown here. This happens to be the Cyrus cylinder from 2,500 years ago. So the first person who discovered this basically had to do a double decoding. It's a double puzzle. Not only the language is unknown and has to be deciphered, but also pieces of the writing are missing and have to be filled in using guesswork, or sort of try to figure out what might have been in the missing part from the context. Once the language is decoded, from the context, we try to figure out what was there that is missing now. And in fact, sometimes the puzzle is almost too difficult to solve because we only have bits and pieces of one of these tablets. And we don't even know how to put those side by side to make the complete tablet. Of course, once the language is understood, so a particular language that was used at the time in history, then other tablets that are discovered using the same language are easier to decode, especially if they are fully intact. If they are not intact, and still because we know the language, it becomes easier to decode them. Now, secret codes are as old as forts, and they serve the same purpose, which is providing security. Okay, let's start with some very simple cryptograms. So basically, these are the simple puzzles we always start with. So there's a cipher shown in red at the top of this slide. And I want to translate it into plain text. Plain text is basically the meaning, the text whose meaning is understood. The text in red, we don't understand. Okay, it looks like garbled message. Okay, in this case, it's reasonable to assume, because of the spacing of the different parts, that this particular message consists of 3 words. Okay, that is not necessarily true, but it's a good guess that there are 3 words in this message. A long word at the beginning on the left side, a short 2-letter word in the middle, and another word on the right. So in order to discover the meaning of this message, we have to know what kind of encoding, what convention is used to encode the message. Okay, so please think about this for a minute or so. I will reveal the answer, but don't advance the video until you have given it a try. Well, this is a very simple encoding or cipher. Basically, the message has been written backwards. So if you read it backwards from the W at the end, you get welcome to cryptography. Well, it's a trivially simple cipher, and it doesn't take much time to decipher it. And any other message that is sent, once I decipher the code, suppose this is something you use to communicate with a friend in secret, once I decipher the code, any other message that you send will be quickly decoded and understood. Here is a second puzzle. Now this time, the red text, the cipher, doesn't seem to be organized as words, because everything has 3 letters, and it's unlikely that all the words in the sentence are 3-letter words. So it seems that the sentence is blocked into 3-letter blocks. It's sort of an additional layer of secrecy that is added into it. So let's see if you can decipher this. Again, spend some time on it before looking at the meaning that I'm going to reveal shortly. Well, these triplets, 3 letters, are reversed, so that EHT stands for THE, the. YPS stands for spy. WSI stands for ISW, that's not a word. But you can probably read this quite easily, because spaces between words have not been honored. It so happens that the first 2 words are 3-letter words. Generally speaking, spacing is not honored, and those random spaces have been inserted. So the spy is wearing a blue coat. That's the message. Okay, here's another cipher in which there is no spacing. Unlike the first 2 puzzles, no space has been inserted between words or between blocks of letters. Well, if this were just an English sentence in which spaces had been removed, you could probably read it quite easily. But this is not an English sentence. It has been scrambled, basically. So what is the scrambling? Again, think about this for a couple of minutes and advance the video to see the answer that I'm going to reveal. It turns out that you can read the plain text message by taking every other letter in the message rather than all the letters. So take I, ignore the next C. Take C, ignore the next R. Take A, ignore the next A. So it says, I can't believe you. And the message continues in the other letters that I ignored in the first part. I can't believe you cracked this code. So basically what the coder has done is taken the message, I can't believe you cracked this code, cut it into two pieces, and then shuffle the two pieces so that letters from the second piece are interleaved or go between letters from the first piece. Again, at first this is difficult to see what has been done, but once you break the code, then reading subsequent messages using the same code becomes very easy. Okay, let's take one more. This looks very much like the second puzzle, but if you try to apply the same scheme, reverse basically, ASS, ESP, XJT, EMS, you don't get any meaningful message. So it's not the same cipher, although superficially it looks like that one. Now this is actually a pretty strong cipher, strong code, because in order to decipher it, you have to know this key that I'm going to reveal. So it's nearly impossible to guess this one, try to solve it without knowing the key. So the key to this one is 74186253. If you know that key, that's basically the order in which you have to rearrange those blocks in order to read the message. In other words, the seventh block, THI, goes first. The fourth block, SME, goes second. Then the first block, then the eighth block. So if you don't know this particular key, you don't know how to rearrange these blocks in order to read the message. But if you don't know the key and you rearrange the blocks, you read the message. This message is top secret. And then the J and X at the end are just to fill the gap to make the length of the message a multiple of 3. So you can easily see that those have been added as padding. They're not part of the message. Okay, here's one last cipher on the slide. This one looks like a regular English sentence. Amy Tan's twins are cute kids. But it's unlikely that that's the message being transmitted, okay? That's the secret message is something that is not what is being transmitted. So this is sort of a good way to throw intruders off because they see this message and say, oh, so something about Amy Tan's twins, nothing dangerous or serious here. Again, think about this, see if you can decipher the message. I'm going to reveal the answer right now. Actually, if you take the first letters of the various words in this message, that's the secret being sent. So the secret in this example is attack. Okay, the There are an endless number of ways you can encode messages. It's just, a matter of your ingenuity and how much work you put into devising the cipher. You can get very strong ciphers, like the next to the last one on this slide. The other ones are not particularly strong because any person putting enough work into deciphering it can probably come up with the secret coding scheme. Okay, one of the oldest ciphers or encoding scheme for secret messages is what we call the substitution cipher. So a substitution cipher basically takes each letter, let's say in the English alphabet. Let's say we are sending messages that are alphabetic. There are no special symbols, there are no numbers. So if they're alphabetic, I take each letter of the English alphabet and change it to a different letter. This is known as substitution cipher. So this is a cipher that looks like a quotation because the first two lines of the cipher, the yellow box and the yellow box, are put in quotation marks. And there's something at the end that is very likely the name of the person who said or wrote this statement. Okay, so it's a quote by somebody we don't know. In this quote, letters have been substituted by different letters. And as a clue, you're told that Z in the message stands for E. In other words, we took all the E letters in the original message and replaced them with Z. Similarly, for all the other letters, we don't know the other ones. This one substitution is given to us to sort of make the puzzle a little bit simpler. Okay, so because we know that part, we start by inserting that knowledge that Z really stands for E. So all the Z's in the message that I've rewritten at the bottom stands for E. It appears that spacing between words has been honored so that one of the clues we can use is that PDZ, for example, PDZ is a three-letter word that ends in E. Okay, well, we can sort of think about all the three-letter words that end in E, and probably the THE comes to mind quickly because that's a common three-letter word in the English language. And that intuition may be reinforced if there's a repetition. So YXZ, for example, YXZ also is a three-letter word ending in E, but there are two instances of YXZ. One up here, and one over here, which makes it quite likely that that's the THE. So this is probably something else. These are just guesses, okay? I can't be sure that these guesses are right. Another angle of attack is try to figure out who this quotation is from. So if you have a name, likely this is the first name, this is the last name, and there's an E in the first name, and there are two E's in the last name. Okay? Think to see if you can come up with a name that has those three E's, one E in the first name and two E's in the last name. Okay, again, I will advance the slide. You may want to sort of pause it here and think about it. Let's not too hard to guess that that's probably Albert Einstein. Not only his name matches those letters, but also he is one of the people that is quoted very often. There are many, many quotes from him. So it's likely that this quote is also from him. So say, okay, let me guess that's Albert Einstein. I may be wrong. There may be another name that has those E's in it, but let me proceed with this assumption. Now, once I've made this assumption that the name is Albert Einstein, I already know a lot of the letters. So let me enter those letters in the message. I know, for example, that P stands for A, B stands for L, L stands for B, and basically the message is almost deciphered. I almost know the entire message. So there are complete words like R, N, A-N, and there are words that are almost complete, like this word over here. What can that word be? Well, it's easy to guess that it might be infinite. Or it's easy to guess that this is the. This is another one. So let's proceed with that assumption. Assume that X is the replacement for H. And basically we make progress from this point on quite easily. So what is this word over here? The third word in the code. Probably things, okay? And so on. And then the message is decoded quite easily. Basically the key observation was to guess this name of the person, code it, and then the rest followed quite easily. And the code reads, only two things are infinite, the universe and human stupidity, and I'm not sure about the former. Of course, if I wanted to communicate this message in secret, it was a very bad idea to write it the way I wrote, put things in code so that everybody can figure out this is a quotation, and put the name at the bottom so that everybody can guess this is a name, and therefore make it easier to decipher the message. Okay, so here is the same message written without those giveaways. Okay, I'm not telling anybody that this is a quotation, and I'm not putting a name at the bottom of it to make it easy to guess what the name is, and therefore a whole bunch of the letters in a message. So how would I attack this? Still, because the word boundaries are honored, I have 3-letter words, I have 2-letter words, 4-letter words, and so on, and those are sort of giveaways. I can try different ideas about what those letters might be. And sometimes repetition of letters is also a giveaway. Okay, so for example, this is a word, the last word in this message has a D here and has a D here, because D is a substitute always for the same letter in these substitution ciphers. I'm looking for a word whose third and sixth letter is a 6-letter word whose third and sixth letters are the same. Okay, or there are other repetitions too. In this 8-letter word over here, in this 8-letter word, there are 3 S's, 2 E's. Okay, so there aren't very many words that have the same letter in the first position, in the fourth position, and in the sixth position. So these are giveaways. Another angle of attack is to count letter frequencies. So in this message, I count the appearances of A. There are 2 of them. Appearances of B, there's just 1. Appearances of E, and so on. It turns out that in the English language, letters are not used with the same frequency. This is a well-known fact, well-studied fact. The letter E is the most frequently used letter in normal texts. The letter T is the second most frequently used. Okay, so armed with this knowledge of frequencies, it's not hard to guess that the letter E is either E, in other words, its replacement is also E. Sometimes we don't allow this kind of substitution, so we can ignore that if we don't allow substituting a letter with itself. So what are the other candidates? S could be E, because there are a lot of S's, and Y can be E, and Z. So instead of 26 options of which letter is replacing E, I have a smaller number of options, only 3, and therefore the job of decoding the message becomes easier. I can take one of those options and proceed with that assumption, and if I get to a dead end that I can't make progress, I go back and use the other options. Also, just as there are letter frequencies in the English language, word frequencies are also clues. So the most frequently used 3-letter words in the English language are the, which is the most frequently used, and second most frequently used, for, was, and his. So these give me clues, right? Because the 3-letter words in the sentence are likely, although not definitely, one of these 3-letter words because they're used often. And sure enough, in this puzzle, YXZ is the, and PDZ is and. So basically, knowledge of letter frequencies and word frequencies allow me to restrict the search space into a much smaller space and be able to sort of go through it much more quickly than if I had to try everything. One last item of information is that letter pairings are also analyzed in the English language, and it was discovered that TH is the most frequently used pair of letters coming next to each other. HE is the next most frequently used, and you can guess sort of that this TH is part of the word the, and this HE is also, because the is so common, the pair TH and the pair HE also quite common. AN probably comes from and, IN, and so on. Okay, so I can count letter pairs. So for example, the pair CE appears here. I can go through the message and see if there are any other CEs. And I find that there aren't. Okay, let's take another one. YX. YX is a pair of letters. Do I have other YXs? I have one here, YX. And let's see, I have another one here. So there are 3 instances of YX. So YX might be one of these frequently used letter pairings. And sure enough, YX is TH. Okay, So this is known as statistical attack. So I use knowledge of statistics of word usage, letter usage, letter pair usage to make a dent, okay, make it easier to decode or decipher such a message. Okay, this is the PIC-pen cipher. So basically in this cipher, letters are replaced by these geometric shapes rather than by other letters. But the idea is the same. This is a substitution cipher with all the weaknesses of such ciphers. In other words, I can still use statistical attack on this because the same letter is always replaced with the same geometric shape. So this square over here, this square over here, this square over here, these two squares are the same letter, okay? So it's not any stronger, despite the fact that it looks a little bit intimidating at first. It's a substitution cipher. By the way, repeated letters are also good clues. So here I have a word that has a repeated letter here. Repeated letters are kind of limited. I can have two L's, two M's, two S's, two T's, and so on. Okay, I don't think I have any word in which there are two J's next to each other. There may be, but it's not common. Okay, so this substitution has a nice property that it's pretty easy to remember. Okay, so here is basically the substitutions that are made. Letters A through Z are written here. And basically, in order to see what geometric shape replaces the letter A, I look to the box where A is located. So for example, the A is located in a box that has this lower line and the right line, but not upper. Oops. Okay, so this is A, lower line and right, lower line and right. L has the left line and lower line with a dot inside. Okay, S is basically this V shape with no dot, and W is V shape with a dot. Okay, so now that makes it easy to, once I know this correspondence, makes it easy to decipher the message. So that's T. Remember, T has this, it's like the greater than symbol. So that's T. The next box is sort of like the Greek pi. It's not this one because it doesn't have a dot. It is this one. So that's H. And proceeding in this way, I can decipher the message. Okay, I've given you a few more clues. Now, question 1 for this lecture is the following. Write the message above in the cipher used for the code on slide 6. In other words, you have to finish deciphering this message, find out what it says, and then encode this message using the cipher or code that we used in slide 6. So go back to slide 6 where the Einstein code was presented and use the same substitution there to encode this message. Of course, emojis are a type of coding, although they're not secret because the meaning of the code is sometimes pretty obvious from the shape of the emoji. Sometimes it's less obvious. So your question 2 to answer is at the bottom of the slide, you see 20 movie titles written in emojis. Okay? And your task is to decode or decipher at least 4 of these movie titles. So for example, if you decipher 1, 5, 7, and 10, just answer those. Say question 2, 1 is this movie, 5 is this movie, and so on. So choose 4 of them that you can decipher and provide that as answer to question 2. This is an extra cipher for those of you who sort of liked this idea of ciphers. In fact, many magazines and newspapers used to carry in their puzzle sections ciphers. Fewer of them do nowadays. But this is from an actual newspaper. It's called Celebrity Cipher. Designer is Luis Campos. And it appears to be, again, a code. And then at the bottom is the name of the person who said or wrote that thing. And then previous solution, of course, means, the previous day or previous week when a puzzle ran, this was the answer. So that doesn't apply to this puzzle. Okay? So you're not required to send me anything for this. Just work on it if you are interested. It's a pretty challenging puzzle. And the name at the bottom is a celebrity, but doesn't say what kind of celebrity. Could be an actor, could be an author, could be a scientist. We don't know. Okay, now let's go to more sophisticated ciphers that are harder to decipher than substitution ciphers that we have been dealing with mostly through the previous slide. So this is a device, a mechanical device, consisting of disks. And around the disks, letters are written. You can rotate these disks. If I show you the wooden version of this, you see the disks. Okay, and there is a rod that goes through the disks, so the disc can be assembled and not put at the end. You can rotate these disks. Okay, and each of these disks has all the letters of the alphabet engraved on it. And if you want to send the message attack at dawn, the secret message attack at dawn, you basically rotate the wheels, the disks, so that that message appears on this row. Okay, so you basically rotate the first one so that A appears here, rotate the second one so that T appears here, and so on. So that's your message, your secret message. And then you transmit the letters that you see on a different row here, like the one highlighted in the green box. So my message that I will send will be CMWDSMXXKE and so on. Okay, so why is this better than substitution cipher? It's a sort of substitution, but the substitution is dictated by the wheel on this mechanism. Notice the letter A that appears here, 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 here. There are 4 A's in the message. in the secret message or coded message, this A has become C. This A has become D. This third A has become X. And that fourth A has become E. So this is not subject to statistical attack. Because if A is a frequently used letter, it will not be always replaced by the same letter, the same frequency. But that statistical property is broken and cannot be used to decipher this message. Similarly, the two T's, the three T's actually, one is replaced by M, one is replaced by W, and the third one by X. Again, even if, by happenstance, there are repetitions there, the repetitions are not perfect. T is not always replaced by the same letter, therefore statistical attacks do not work. So spies who want to use this device, each of them has a copy of this device and then uses it to encode the message, sends the encoded message, and the other spy, which has an identical device, basically turns the wheels until this secret message is generated on one of the rows, and then looks around to see if there is something meaningful in any of the other rows. So once this row has been constructed, it's not too hard to notice that this row contains a meaningful message, and therefore that's the secret message. All the other ones just seem to have just random letters. Okay, now the nice thing about this device is that once you have used it for a while, you can rearrange the wheels, just disassemble it and put the wheels or the disks in a different order by mutual agreement with the recipient of your messages. And then the code basically changes. So if somebody actually even discovers this device, somebody comes and searches your home and discovers this device, that is good enough only for breaking codes with its current arrangement. Okay, if you take the device and rearrange the wheels, a person who doesn't know what rearrangement you use, so the rearrangement is basically a sequence of numbers. Okay, so you say the wheels are numbered 1, 2, 3, and so on. And then you say, okay, the wheels should be placed in order 5, 9, 22, and so on. Some random, hard to discover ordering. So the secret is basically safe. Now, one of the most interesting devices to use for coding using these kinds of substitution, not letter by letter substitution, but a very sophisticated substitution, was the German Enigma machine that the German Navy used in their submarines. And they could send messages to submarines without the Allies being able to, even if they intercepted the messages, they wouldn't be able to understand what they said. Okay, so this Enigma machine, let me take a few because it's very interesting, consisted of various components. There was a keyboard right here, the standard typewriter computer keyboard, QWERTY keyboard. Actually, it's not QWERTY, it's QWERT, the Y is replaced by Z. It's a slightly different arrangement. So there's a keyboard. So when you want to send a letter in your message, you press the key. So if your message begins with W, you press W. When you press W, a circuit is established. So this is a battery. Circuit is established and is connected to this plug board. So plugboard is basically a replica of the keyboard, but it doesn't have keys. It has holes. And this W is connected by a piece of wire to this key at the bottom, which happens to be X. So W is connected to X. So basically W is replaced by X. And this X is transmitted through the circuit over here. And these are basically permuting wheels so that the letter X is replaced with some other letter. So internally there are wire connections between the letter X on the input and perhaps the letter P on the output. Those wires are invisible, they're inside. And then if that's the letter P, in the second wheel another replacement occurs. In the third wheel another replacement occurs. And then the circuit goes backwards, one more replacement, yet another replacement. So there's 6 replacements here. So the ladder is totally scrambled. We have no idea what comes out of this other end. It goes back to the plug board. It's substituted with a different letter. So this is H and this is I. So the light associated with the letter I will light up. So when you press the key W, the I light will go on, and the transmitter knows that he or she has to transmit I instead of W. Then you press another key, similarly you get a different letter. So if you press W twice, the first time it will generate I. If nothing in the machine changes, the second time also I will be generated. But these wheels actually move between pressing of the keys. So I'll show you the actual machine, the physical machine in a minute. So these are cogged wheels that move after pressing each key. So the next time you press the key W, another light will light up. And furthermore, even the operator does not know what code is being used because these connections inside those wheels, so these wheels were manufactured at the German Army headquarters and were sent to submarines. The wiring inside them were unknown even to machine operators. So the machine operator, basically like a robot, would press keys, observe which lights go on, and substitute that letter for the intended letter. Now to make things more challenging, so this process is described here. Step 1, W is pressed. Step 2, battery connected to W, which is wired to X on the plug board. And then connection goes to the 3 rotors, or these wheels. So any substitutions take place there. And then finally, the I light is illuminated. Okay, so this is a replica of the machine. That is in some museum today. I don't know if any of the actual machines have survived, but this is a sort of exact replica of the machine. So here's the keyboard. Here's the plug board. Here is the light board where letters would light up. Here are the 3 wheels. And these 3 wheels can be initialized to a particular state before operating the machine. So for example, part of the instruction to the operator of the machine in the morning was use the setting 0226, let's say 16. So this code would be sent, the wheels would be turned so that that particular setting appears in these windows. So that's initialization, basically. So even if someone had this exact machine, suppose one submarine was captured and the Allies actually had the machine, if they did not know this initialization, they probably would not be able to decode the messages that they intercepted. Okay, during the Second World War, the British had this huge operation at Bletchley Park where Alan Turing, a mathematician, and in those days we didn't have computer scientists, but he was one of the first computer scientists, people who worked on computer science. They worked on basically discovering this code, and they eventually succeeded and broke the code, which was very surprising given how strong the code was. The life story of Alan Turing, at least the part connected to this code-breaking activity, was the subject of the Imitation Game, a movie. Of course, like all movies, it wasn't completely accurate, but it reflected, the effort that he and his co-workers put into breaking this code. Some of my slides have videos embedded in them. I won't show you the videos, but if you're interested, this is a video that discusses how accurate the Imitation Game biopic was, how accurately it reflected the life story of Alan Turing. And this video is a brief demo of Enigma. So in this video, you see the machine in action. Somebody is actually using it. So it's interesting. Please watch that video. It's only a few minutes. This brings me to question 3. I'm asking you to write a short paragraph about how the Allies managed to break the Enigma code. A short paragraph means maybe 5 or 6 lines, not too much detail. Basically, what was the key observation, the key idea they used? And you can use the internet resources to answer this question. The answer is not in the slides. So basically do a few searches and see if you can discover how the code was broken, and report your finding to me in a short paragraph. Okay, the next idea is key-based ciphers. Okay, of course, this sophisticated Enigma machine, for a military, it's easy to build those and use them, but we want the cheaper method to be able to encode messages securely. So key-based ciphers provide this capability. Okay, so what is a key-based cipher? Let's say I assign codes 0 through 25 to the letters A through Z, numerical code. So that if I want to write a message using letters, I can use those numbers instead. Of course, that doesn't make it secret because the correspondence between numbers and letters is easy to discover. Then we agree on a secret key, for example, R key. So if you and I are trying to transmit secret messages, we say, okay, let's agree on this key, which is easy to remember, R key, OURKEY. So let's take a plain text, which is attack at dawn, and write it as, replace each letter with its numerical code. So A is 0, T is 19, T is 19, and so on. So this is my secret message in this numerical code. And then write down the key, our key, and repeat it if needed until the length of this string is as long as the message. So I don't want to make this key too long so that it's not difficult to remember. I could have chosen a much longer key. But my key is only 6 letters long, and the message is 12 letters, so I have to repeat. Okay, I repeat the key as many times as needed to match the length of the message. So this is this repeated key in numerical form. O is 14. Here I don't make a distinction between lowercase and uppercase. Okay, I could have made that, but we're not making that distinction. U is 20, R is 17, and so on. So here's now the coding process. I'm going to add the code for the message letter A to the code for the key letter O. So 0 plus 14 is 14. 19 plus 20 is 39, and so on. And I do modulo 26 reduction. In other words, whenever the number is 26 or larger, I subtract 26 from it. So 39 becomes 13, 36 becomes 10. So these are all now numbers between 0 and 25. And I can replace them by the letters associated with them. So 14 is O, 13 is N, and so on. And this will be my secret message. ONKKGION. So pretty much impossible to understand unless someone has this key. If someone does not have this key, they won't know what kind of substitutions were made here. And that key, of course, has to be protected, like a password that you protect. That key must be protected because if somebody discovers your key, they can decode all your secret messages. And then if I want to decode this secret message over here, I do the reverse. This is my secret key, repeat it twice. Okay, I do subtraction. 14 minus 14 is 0. 13 minus 20 is negative 7. 10 minus 17 is negative 7. And then I do again modulo 26. In other words, if the number is less than 0, I add 26 to it. So add 26 to negative 7 to get 19. Add 26 to negative 16 to get 10. And then this is basically the plain text, the original message. So I added the key modulo 26, and then I subtracted the key modulo 26 to get the original message back. So as long as you have this key, you can encode messages and send them, and you can decode received messages. Okay, so I'm going to skip the slide, except to show you question 4. Question 4. Show the encoding and decoding of the message I sent an attendance report for ECE 1B. The quotation marks are not part of the message. And ignore blanks. Okay, we don't have a code for blank. So just encode the letters. I sent an attendance report for ECE 1B. Use the key, my key-based cipher. Okay, so using this key, encode the message I sent an attendance report for ECE 1B, ignoring the blanks. And then send me as answer to question 4 the ciphertext, okay, the coded message, what the coded message becomes. Of course, in computers and communications, we have binary messages. Everything is in binary. So instead of encoding letters, and I've included a few special symbols here to show you that they can be included if you want to. So there are 32 symbols, 26 letters, and 6 special symbols that are given codes 0 to 31. Now those numbers happen to have 5-bit binary representations, and our agreed upon secret key is also a binary string of zeros and ones. And then I can use, so here's my plain text. So what is the plain text? It's a bunch of zeros and ones, but it represents 00111, which is 7 in binary, that represents H. 00100, which is 4 in binary, represents 4. And 11000, which is 24 in binary, represents Y. So the message is hey, H-E-Y. So that's the secret key inside the red dashed box. I've repeated the first 4 bits of it in order to make it long enough. Okay? And then the encoding is basically XOR, or modulo 2 addition. So basically I say 0 plus 0 is 0, 0 plus 1 is 1, and so on. 1 plus 1 is 2, modulo 2 is 0. So it's basically addition, except whenever the sum is 2, I replace it with 0. So this is now the secret message that will be transmitted. Again, if somebody does not know this key, they won't be able to understand what this message is. But if somebody has the key, including the recipient, so the message will be basically PZ sharp, which is nonsensical, okay? But if somebody has the key, the nice thing about this binary code is that the decoding is exactly the same process. Remember, in the previous code, I added modulo 26 and then subtracted modulo 26. Well, modulo 2 addition and subtraction are basically the same. So here's my secret key, repeat it partially to make it long enough. And now I XOR the secret message with this key. 0 plus 0 is 0. 1 plus 1 is 2, which is 0 modulo 2, and so on. So this is the original message. So this is known as a symmetric encoding and decoding. The encoding and decoding process are basically the same process. Now, in actual usage, we have something called data encryption standard, which uses hardware to do the encoding for us. So given a message M, I split it into 2 halves. So if this is, let's say, 1024 bits long, this half will be 512 bits long. This half will be 512 bits long. And I use a key, a secret key. And this box computes a function of this mi and k. So that function basically is easy to implement in hardware, but it's pretty complicated to reverse engineer. So if you know this output, okay, unless you know this key, even sometimes when you know the key, you cannot reconstruct mi because you cannot go backwards. But at the very least, you have to know this key in order to find out what the information was that was encoded. And then you take this 512 bits and this 512 bits and XOR them. And then repeat this process several times to make it even harder to decipher. So this is a hardware encryption device into which you input your message, And then it basically does all sorts of shuffling and replacements and these function computations to give you something at the output that it's almost impossible to understand or break without knowing all these keys, K1, K2, K3, K4. Okay, so basically cryptography, or the secret encoding of messages, is some sort of transformation that you apply to plain text to get the ciphertext. And this should be a fairly complicated function. And in particular, it should be a function that is unknown to intruders and interceptors of your message, and should not have an inverse function. Okay, so let's say this is a number x, and this function is squaring. So if I want to send the number 5, I square it and send 25. Well, squaring has a simple inverse function, which is square rooting. And if somebody knows that this is squaring, can easily take the square root of 25 and discover the original message. In fact, one of the fears of people using encryption for secret communication is that the person who designed this encryption, it's pretty hard for an ordinary person to break the cipher, but the person who designed it could have provided a backdoor, a secret channel, like an inverse function, that makes it easy. So often, for example, people say if an encryption standard is approved by the government, maybe the government has this backdoor, so that whereas I think that my message is secure and secret, the government can intercept it and use this simple inverse function to discover what the message was. There are all sorts of conspiracy theories in this regard. Of course, this is not a totally unfounded suspicion, but there are so many different encryption schemes that it's unlikely that the government or some secret organization has the backdoor for all of those. Okay, this is sort of an analog of a magician putting on handcuffs that look genuine and then go into, a bag or a water tank in which he would die, in a matter of minutes if he cannot get out of those. But these handcuffs almost invariably have a secret latch that opens them, and that latch is invisible. You can't see it. Even if you go up close and examine it, you may not see the latch. So that latch allows the magician to get out of the handcuffs quite easily. That's sort of like the analog of this backdoor. Okay, a couple of final ideas. There's this method of cryptography called public key cryptography. Now, when you have cryptography based on keys, that key can be a nuisance because you have to communicate the key. So once in a while, for example, you may want to change the key. And then you have to communicate with the other side what the new key is. Well, how do you communicate? You have to make a phone call, write a letter, and those can easily be intercepted, and therefore your key will be known to the interceptor, and therefore your messages are no longer secure. So it would be nice if we can have keyed cryptography without actually having to communicate key. And public key cryptography does that. Each person has two keys, okay? A public key and a private key. And those are generated by a key-making function. So Alice chooses a random sequence, feeds it to this key-making function, and out come her public key and her private key. She keeps the private key to herself, But the public key is published. It's like a phone number. You can publish it in a public key book, similar to phone book or in some website. So everybody knows Alice's public key, but only Alice knows her private key. Okay? Now these keys are chosen such that, and that's non-trivial. Okay? I won't explain to you. There's the next slide that has some details if you are interested, but I won't explain to you how these are made so that this property is maintained. So whenever Bob wants to send a secret message to Alice, he uses Alice's public key that is known to everybody to encrypt the message. So this is the encrypted message. Now, if somebody intercepts this encrypted message, he or she would not be able to discover the original message. So this is sort of a one-way function. You provide an input, you get the output, but from the output, you can't go to input, even though everybody knows this key that was used. So this one-way function, that's part of the features of this scheme. And then Alice receives the encrypted message, uses her key, her private key, to decrypt it. And nobody else can decrypt the message because they don't have this private key. Okay, so encryption is done with public key. So no key needs to be, no secret key needs to be communicated. This one everybody knows. It's decided once and it's published for everybody to see. And this one is kept just by Alice and it's not communicated to anybody else. Okay, we can use this scheme also to sign documents. So suppose Alice wants to promise Bob that she will pay $500 for whatever deal they made. So she uses her own private key to encrypt the message. This is the encrypted message. Again, somebody who intercepts this message will not know what the original message was. This message goes to Bob, and Bob uses Alice's public key to verify that this message was indeed sent by Alice. In other words, it's an authentic message. Nobody forged it, okay? So because nobody else has Alice's key, they can't forge messages and pretend that those messages were signed by Alice. Only Alice can sign messages. Okay, of course, everybody has this public key, so everybody can decode this message. So this is not a mechanism for secret communication. Okay, everybody who receives this can decode it. I think I said before that they can't. I'm sorry, I made a mistake. Everybody can decode that, but this is not a secret message. It's just a promise to pay $500. But Bob has to verify that this message actually came from Alice and not from somebody else impersonating Alice. Okay, so it's a signature. The message has a signature. Okay, I'm going to skip the next part of this slide and just show you this analogy. So the analogy of public versus private key in this slide is assume that Alice wants to send a secret message to Bob, and that secret message is placed in this box. Of course, you know, somebody who gets hold of this box can break it and remove the secret message. Let's say that's not an option. You have to have a key to the box in order to open it. She sends the box over to Bob. Bob has his private key, and only he has this private key that can open this box. Alice used one of these public padlocks associated with Bob to lock it. If she wanted to send a message to, let's say, Dave, she would have used one of Dave's padlocks. In other words, the public key for Dave. And then only Dave would have been able to open it. It's not a perfect analogy, but sort of like gives you the feel for why it is that, you know, everybody knows the public key, but that doesn't compromise the information. Only Bob has his own private key that he can use to open this box. Okay, as I said, the last slide contains a description of how this can actually be implemented, and I'm not going to go through that one. Okay, so this is the end of the lecture. Please, so this lecture is scheduled to be presented originally in class on April 20th, Monday, April 20th. And your attendance report for it is due by 6:30 p.m. Wednesday, April 22nd. Okay? Bye for now.